Hey everybody, this is Larry. This is week 2 of the premium Leetcode weekly challenge, something like this. Hit the like button, hit the subscribe button, join me in Discord, let me know what you think about this one. So we have 351 Android unlock patterns, and as you can see, I have not done this problem yet, so I'm excited. Let's see. Android devices have a special lock screen 3 times 3 grid or 3 by 3 grid of dots. They could send unlock pattern. I actually haven't had an Android in I think I last bought an Android phone in like 2011 or something like this. So that is a crazy amount of time ago. It was a very beautiful Samsung phone, uh, but I don't know what happened to it. The battery life was terrible, so I had issue with that one. And then at some point, I think I just got an iPhone for some reason, and never went back. I don't know. I don't know if this is an interesting story, but it is kind of related, I guess. Anyway, it's been a while. My pattern was really dumb, so I don't even remember it. Lucky I don't need to. Okay, anyway, connecting the dots, a sequence of k dots is a valid unlock pattern if both of these things are true, or the dots are distinct. So, okay, so the same dot does not appear more than once. Or line connect pass through the center of any other dot. The other dot must previously okay, so you can jump across a dot, which I guess you look in the okay. Can you go from like what is that 1 to 8 like a 2 by 1 thing? No, I guess you can because here there is what is it 9 to 2. Okay. Connecting dots 1 and 3 without dots and 2 because the line. Okay, yeah. Okay, fine. Given two integers m and n, return the number of unique valid unlock patterns that consist of at least m keys and at most n keys. Okay. I mean, first thing, m and n is terrible, so let's go this. I don't know. A and B is that's confusing. I don't know, but the way that the first it's only 9 anyway, so you can definitely brute force some stuff. But the way I would also always think about these things is that basically now the first thing you should think about, or it comes up a lot, is that now you're given a range, right? So basically, at most n keys, what does that mean? That means that at most b keys. Okay, let's keep it m and n because I think I'm just going to confuse myself. Okay, and most, I thought it was going to be rows and columns. That's why I was like going to change it, but then it doesn't make sense anymore. And most n keys means that we have some like f of 0 key, which doesn't make sense probably. But f of 1 key plus the count of 2 keys plus f of 3 keys plus dot 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 plus f of n keys, right? And then what was the other one? At least m keys. At least m keys is then now f of m plus f of m plus 1 plus f of m plus 2 plus dot 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 plus, you know, to infinity, I guess, right? And then now, right? And of course, I don't know why I wrote it this way actually, so maybe this is a little bit confusing. My apologies. But now we want to have. Okay, yeah, the way I wrote it is a little bit weird. I mean, it's precise, but it's a little bit weird. So now we want at least m keys and at most n keys, right? So then now what we want is f of m plus f of m plus 1 plus f of m plus 2 plus dot 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 plus f of n minus 1 plus f of n, right? Something like this. And of course, let's actually skip this one, but this one makes sense, right? So then now you can say that, well, this contains this, and then now if you add another thing, just say at most m minus 1 keys is going to be f of 1 plus f of 2 plus f of 3 plus dot 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 plus f of m minus 1, right? And then now, of course, you know, you can maybe just stretch this out. We can say that n is greater than m, say. Then now you can see that this is going to be f of m minus 1 plus f of m plus f of m plus 1 plus dot dot dot. I'm just going to dot it out. But the key point is that if you subtract this from this, or the other way around, if you subtract this from this, then you get this, right? So that's basically the idea. It comes up a lot. It makes problems easier to solve because now you don't have to solve in some like weird. I mean, for some problems you might still, but at least now this is the sequence that you want. So then now maybe you can return like f of what did I say? F of not f, because f is just the function for 1. So maybe you have like a prefix, which is the sum of all these things. So maybe you have like maybe sum. I don't know. Whatever. Either way, is equal to this. And p of m minus 1 is equal to this, then now this is just equal to p of n minus p of m minus 1, right? So this part I think should be okay, and yeah, it is at least 1 anyway. The way they did this is a little bit awkward because it doesn't seem like it's strict that m is greater than n. Or it's the other way around, n is greater than m. So here maybe we just want to add something like max is equal to 0. I mean, you could do this in a number of ways. You can do an if statement or whatever, but this should be good enough because otherwise we're at negative if m is greater than n or something like this. Right? Anyway, okay. So hopefully you took these notes. I'm going to delete them. I'll just put it in the bottom. But yeah, and then now we have to define this p, right? So p of x keys. How do we want to do it? I mean, this part, it's a little bit straightforward so far because now we want to do at most n keys, right? So it's these things. Yeah. So also, I just want to say one thing is that there are more direction to this, but they're only by symmetry, there are only a couple moves you can make. You can make one-step moves, up, down, left, right, and diagonals. And then the two-step moves are only the horse moves, right? Well, not a knight move. Sorry, I sometimes I call a knight a horse. Like in chess, you have a knight's move, and it looks like a horse, right? So I call it a horse move. But a knight move, right? Which means like 2 by 1, and that's the only other move. So yeah, so up, down, left, right, and then 2 by 1, or whatever it's called, the knight's move. So yeah, but anyway, I'm just trying to think what is the cleaner way of doing this, right? Like we can definitely, like one way to write it is just write it out this formula, right? And that's fine. But I think we can actually, you could do a dynamic programming and it's a little bit cleaner too, but yeah. Yeah, like you could write a for loop and then just do it one by one, but then you have this like n square thing, which is a little bit awkward because I think you could just do it with one dynamic programming. So so maybe the way that this is structured, so maybe this is one of the few problems where this doesn't make as much sense. But that said, you can also pre-calculate these, so I think that's fine, right? So for example, yeah, okay, fine. So for example, maybe you could write something like for I in range of from 1 to x plus 1, so that's x inclusive. Yeah, let's just keep it simple. So write it this way, so we're f of I, and of course this is what we said f would be, right? Is that what we want? I think I have to change this up a little bit, but you'll see why in a sec. Because I actually don't. No, I think this is fine. Yeah, I mean, I think this is good, right? So we have f of x, right? And now f is good. So p is return the number of patterns with X or fewer keys, right? And here is return the number of patterns with exactly X keys, right? And I know that I'm overdoing this a bit. I think the dynamic programming is actually pretty straightforward. But I think the way I'm doing it has more carryover or generalized a little bit better for other problems. So I don't know. Maybe not. Let me know in the comments. I don't know. Right. Yeah. Okay. So then what does this mean, right? So now. Yeah. So then now we want to return. So this is the total number of patterns, right? So then maybe we have something like grid is equal to g of x. And then now we sum up the total. I'll explain what I mean in a second. Hang on, right? Okay, so something like this. And now we have another function g, right? Which is a little bit different. So here, what we want is going to be return the number of patterns that ends with that ends on each cell, right? Is it going to be 3 by 3? And then it's just okay. So now this should return a 3 by 3 grid. Return a 3 by 3 grid where yeah, where the value of each cell, right? Something like this. I don't know. I think I'm saying this a little bit awkward, but hopefully that makes sense. Yeah, the phrasing is a little bit awkward, but yeah. I mean, hopefully with code you'll see, right? And here, so then now, what do we want to do, right? This is classic dynamic programming, and of course also we should cache this. We'll talk about this later. There is some nuance about that with respect to whatever, but it should be okay. I mean, what I mean is that because here, what you want to do is cache this, but this you're gonna cache a reference, which is a little bit awkward. These are things that you know when you realize when you have a lot of experience. You might, not realize it, but yeah. Anyway, so then here, if x is equal to 1, then we just return a grid of all ones, right? Because just one dot on. You just have one dot, so it's just cell of 1. So then here, maybe we can return something like, and you can maybe write this in a for loop. Maybe I'm a little bit lazy. I just kind of want to, like this is a cool visualization. Maybe I don't know if that's true. At least for 3 by 3, this is fine. I don't know. Maybe we could still write double for loops. But yeah, so that if x is equal to 1, we have this, right? And then now, if x is greater than 1, what happens? Well, then we want to get the x minus 1, right? So previous grid is equal to this, and then now we want to do the current grid is equal to, let's just say this for now, right? And then we return current. And then now we just simulate or do the math on, okay, now the number of ways from the previous grid is equal to whatever, and then we have to make one move to some, oh wait, I think I messed this up. I think I messed this up because I try to be too cool. The reason why I messed this up is because I forgot that each dot in the sequence are distinct. So you can't do it this way. Sorry, friends. I think I messed up. My fault. Yeah, I mean, no, you can't. I forgot. Okay. Okay. I mean, even Larry makes mistakes. I forgot about this. That's all. So yeah, because of the distinctness, you have to maintain the states, which means that you cannot use dynamic programming, which is kind of what we did here. But this is kind of a cool way to think about it. I think, I mean, this is not going to be the right answer because this is not for this problem. There's no distinct. But I'm going to finish typing it out a little bit just so that you have an idea of what it would look like if the dots doesn't have to be distinct. Then you have this like dynamic programming per level. And it, I think it's a pretty cool way of doing it, honestly. But yeah, if you want the actual solution for this problem, maybe skip ahead because that's my fault. I mean, I did read it, but I just kind of didn't occur to me, and because I was just thinking down this grid. But yeah, but basically now it's just that, okay, each previous move cell can move up, move in two ways, right? Up, down, left, right, right? So here we have for x in range of 3, for y in range of 3, and then now we want to say, okay, so we're at xy, or the previous cell, is on xy, and then we want to, how many cells can it go in the pattern, right? So then now we go up, down, left, right, right? So we can set directions, right? And here we can reuse later anyway, so maybe this is good. Because this is universally true. So then it's just all the up, down, left, right, and the diagonal. So you have 8 cardinal moves, and this is dx, this is dy. Yeah, there are a couple of ways you can write it. As long as you write all the cases, it should be good. As long as you're consistent. Which sometimes it's easy to not and miss things out, right? But anyway, so there's this, and then yeah, just all the 8 directions, right? So these are the 8 directions. Oops, is that right? No, that's right. Yeah, these are the 8 directions, and then now you have to do the horsey moves, right? So yeah, that's a little bit annoying actually. So now you have this, the mirror, and then just the other way, I suppose. Yeah, let's just do this. I mean, it doesn't really matter as long as you're consistent with your things. So yeah, and these are the horsey moves or knight moves, I know. Yeah, right. So then now you have 16 moves for this direction. And then it's just about, okay, well, now you have this transition in dynamic programming. So current, actually, you have for dx, dy in directions, you have nx and y is equal to x plus dx, y plus dy. If nx and y, this is less, nx is less than 3, basically if it's inside, oops, I so used to writing it that way. Then now current of nx and y, we added to the previous of nx of xy, and then that's it. This is actually pretty beautiful, and you could even cache it and it'll be fine. I guess for 1 and 2 it makes sense, because for 1 and that's actually kind of good check. For 1 and 2 it makes sense because the distinctness doesn't come up, right? Because well, for 1 dot it's just 9 because you have 1 on each one, and then for 2 dots you make 1 move, so you can't go back to the same move. But for 3 it's going to be wrong, just because, well, yeah, just because I have and I think for these kind of problems, sometimes getting a wrong answer actually gives you a hint depending on how it is wrong, right? So here I don't know what the right answer for the problem would be if it is not distinct, but now that I know that it's distinct, I mean, I knew it before we implemented it, but I know that we overcount, right? Because we overcount because we go back, we count patterns where you can go back to the same numbers. So that means that we expect this output to be greater than the expected. Because, for example, if this gives me 200 or something, and it's lower than 385, that means that our hypothesis is wrong, and that means that something is really wrong in addition to the misreading, because we expect our number to be higher than the answer, right? So these are kind of the debugging mindset that you get used to. But in any case, yeah, this is clearly not the great way to do it, right? Because, well, it has to be distinct. So yeah, so this is kind of cool though. I mean, yeah, and you can, and the other thing is that I know that I wrote it this way, but you can actually do memorization on this. So then now everything is just calculated once, and also as a result of that, you can save it, and yeah, and it'll be fine over different test cases, because doesn't really even matter. Okay, so now yeah, we have to kind of change how we want to write it, right? And of course, because of the distinctness, there really no other way other than brute force, right? So you can, there are a couple of ways you can maybe think about this, but the thing is that in the worst case, it's going to be 9 factorial because there's 9 cells, and yeah, 9 factorial. I mean, not all of them are routed for obvious reasons, like, you know, like even just in the here, right? But 9 factorial is an upper bound, and of course, that is going to be just 362,000 and 880 or something, right? 9 factorial. And even on this one, you can actually memorization, right? Yeah, I mean, I'm going to do it once without memorization, but then I'll do one with the memorization just so that you can kind of see what it is. But my apologies that we spent 20 minutes on the wrong solution. But like I said, I think there are some cool ideas to get from this with respect to, you know, just transitions, because I can see that there are similar problems to this where you know, you don't have this distinct thing, and so, you know, like you know, they're like chessboard problems, for example, like how many like if you have the same problem with chessboards but no, you don't have to worry about the distinctness, then this would give you the answer, right? Anyway, but that's not the case here. So yeah, so let's do it with yeah, I mean, yeah, um yeah. Let me think how I want to write it in a more generalized way. Because I'm also trying to incorporate the dynamic programming, but maybe that's too advanced, or like I'm too lazy. Maybe that's the bigger thing. Okay, fine, right? So here, yeah, I mean, I think it does. I mean, you can definitely still squeeze it in like this, but I think it doesn't make sense. So I think we can just, you know, run the brute force and then just see how many are within M and N. There are some things that you can do, which we'll play around in a sec, right? But yeah, okay. And we'll keep the direction just because that is the way the things go, right? So then now here, yeah. Okay, fine. Let's just write in. I'm trying to. The reason why I'm pausing is because I think I'm trying to prematurely optimize it too much, which I probably shouldn't, especially for teaching people at home. So, I mean, it's just brute force, right? With these other direction things. There are a lot of directions, actually. I guess 8 plus 8 is 16, but most of them are obviously not routed because they go outside, right? But yeah, okay, so then, yeah, yeah. Let's just say we have, so we have a you know, naming things are always hard. I just go and move. I'm lazy. So then now we're currently at XY, and we already made, we have a scene array, right? You know, yeah, scene array, or matrix, I guess. And then what else? And then I guess just moves. I mean, the moves is not that important because you can calculate moves from scene, but you know, it's just a little bit easier, right? And then now maybe we have a answer is equal to 0. Is yeah, if moves is between M and N, then answer plus 1. And I'm gonna go answer. You want to keep going though, because you know. But yeah, and then if moves is greater than N, then we just return because early termination, though, whatever. But yeah, and then it's just for dx dy in directions. Nx, I guess I shouldn't have deleted because I wrote this already. And then it's not that big of a deal, right? as you can see. It's very easy. Get more practice in, right? And scene of nx and y is not true, so we haven't seen it yet. Then we want to set the scene to true. This is backtracking, by the way. I don't know if I said that explicitly because I don't know. I just, in my mind, I call it something else. Scene and then moves +1, right? That's pretty much it. This is classic backtrack. And then now we say, yeah, we start at each one, right? So for x in range of 3, we want to say move xy, I guess scene, and then moves is one move, I suppose. We start with one move, yeah. And then of course scene is going to be equal to force times 3 for range of 3. So this time I didn't write it out. And that's pretty much it. And my watch is telling me to get up for my work. Okay, so you could try 1, 3, 1 to 9, and I mean, if it gets 1 to 9, I think I'm pretty confident about it. It may be pretty slow though. So here we double count. Why do we double count? Dong dong dong. Well, ironically, this is the same number that we got from the other problem. So that means that we're going to the same place. But I thought we handled this, right? Like we don't double count. Well, it's wrong for that particular one in a very specific way because we did not set the first cell. So in a way, we don't double count because of this, except for we double count the first cell because we forgot to set this one. Okay. Oh well. And now we undercount. Huh. Dong dong dong. Why are we undercounting? Am I missing one of these things? It may be. This is up, down, left, right. Should be okay. The 8 directions. And then the 8 knight moves. It looks what I would expect. Huh. Honestly, I'm a little bit stumped. I thought this would be okay. So it works for 2 and 1 and 2, but 1 is trivial and 2 doesn't have any doubling. But here, am I overcounting some stuff? Or undercounting some stuff? But this is the only way that this would be true. But I don't know how that would make it. I must have some typo. It's either that or this is duplicate, but there's no way this is duping anything. It's either that or I misunderstood this problem a little bit. 7 to thing is fine, right? And 8 to whatever is fine. Right? Oh, so, oh man, I didn't read this one properly. I guess, you know, if I see that, I thought that you just can't pass through the center of every other dot. And that maybe is why I'm undercounting. But it seems like you can pass through the center of the dots if they already exist. there are only two ways to go through the center of a move anyway, which is if you go 2 by 2. So okay, so we could count that, I guess, right? So like, I guess we could do it manually, right? Oh, you can also, and yeah, okay, fine. So then now we have for dx in, this is a very awkward thing, I guess. Maybe this is why, I mean, it's not that hard, but yeah, something like this. But there is a special thing, right? So then now, if dx is equal to 0 and dy is equal to 0, we continue because then we don't move. Otherwise, if one of them has to be a 2, right? And we have, well, first check that it is in bounds. So yeah, if I mean, it's not hard, but I think I just didn't read the problem correctly, and yeah, it's hard to read. But yeah, so okay, and then now is equal to this, right? So this is inbound, and then the midway of it. So maybe this is equal to x plus dx divided by 2, y plus dy divided by 2, and we know that it's just this should be good because these are all even numbers, right? So yeah, so then now not seen and seen of mx and my. By definition, we don't have to check the bound again because this is in the midpoint of nx and y, right? So if nx and y is inbound, then the midpoint is not going to be outbound. So then now we do this thing about, yeah. Man, I did not read this problem correctly, I'm not gonna lie. So that is on me. And you could probably kind of rewrite this a little bit cleaner, but let's get it correct first. Yeah, I mean, it looks okay, so let's give it a submit. If it times out, the optimizations we could do, but yeah. Yeah. That is annoying, actually, to be honest. But yeah. I mean, I don't think, I mean, this is just regular backtracking. I think at this point, we do so many dx dys that we might as well just do check every cell and then just do it backwards, I think, almost, which is very awkward. Like here, we check 16 things plus 9 things. So that's 25 things for a cell that is 9 cells. So you can probably do some optimization about that and just check every cell, right? Check every 9 cell, like for like at this point. Okay, so let's actually play around some optimizations, and of course you can actually do dynamic programming on this as well, but you don't even need to really, because there are only 9 possible answers. But first we'll cut this down just because I don't know, it's for nx in range of 3, for ny in range of 3. If x is equal to nx and y is equal to ny, then we haven't moved, so we continue. Otherwise, yeah. Yeah, then dx dy, we go back. So dx dy is equal to x. I guess it doesn't really matter. I mean, it's consistent, but yeah. Minus x and y minus y, right? So then now, yeah. Well, first of all, we want to see that even before this, now we don't have to check our bounds at least. If not seen of nx and y, or if this is seen, we continue, right? Because we've already seen this, or we already made that move. So then now dx dy is equal to this thing, right? Whooping my eyes. Dx dy is equal to this thing, right? So which is that if dx mod 2 is equal to 0 and dy mod 2 is equal to 0, this is so that we check the middle point like we do here, right? Then let's just do it this way. Mx my is equal to x plus dx over 2, y plus dy over 2, right? So then now if not seen of mx and y. So if the midpoint is not seen, then we continue, right? Otherwise, we're good to go in nx and y. So then we just go seen nx and y is equal to true. Seen nx and y is equal to false. And then we just, what's it called? Move nx and y, seen moves plus 1. If nothing else, the code is a little bit cleaner or shorter or whatever. So yeah, give a spin. I don't know if this is that much faster, honestly. We'll see. You just do a lot fewer if statements, if nothing else. Yeah, so that's one. But the other thing that you can do is just noting that the answers are the same across different test cases. So maybe you can do something in the global space, which is kind of silly that Leetcode lets you do this, but it is what it is. Then you can maybe write something like answer, right? So then now you can write, or just like cache is equal to this. Then if length of cache is equal to 0, then we just kind of run this code, right? And what we want here is that if I mean that's it, we don't even need this because it goes up to 9 and then just doesn't recurse anymore. But here we can write cache of moves increment by 1. Cache is equal to 0 times 9. Let's just say 10 because I think it goes from 1 to 9 instead, right? So then now we can do this, and then now the answer is just return sum of cache from n to n plus 1. Oops, I think I just delete this anyway. How do I write that? Is that global? Yeah, and then of course the big one is 1, 9 anyway, but yeah, so let's give it a submit. So yeah, as you can see, because this makes it so that we only use it once, so we don't recalculate anything. We just do it once over for all the test cases. Yeah, and like I said, in the worst case, it's still gonna be 9 factorial, so which is really not a big issue. Yeah, maybe I should go this should go first. I don't know. That's a really minor optimization. But yeah, you can also use bitmask dynamic programming is the one that I didn't talk about. Definitely if you want to upsolve it, do it that way. I don't know. I'm curious. Adjacent move diagonal, extended moves, move skipping dots. Okay, backtracking. I guess I did backtracking. Backtracking optimized. Yeah, we can move that's basically what I did. I actually did this optimization, as you recall. I don't know what this code is though. Their code seems way more intense than the way that I did it. But memorization, yeah, as I said, you can memorize with dynamic with bitmask DP, which is fine. This is a stupid way to write O of 1, but that's fine, I suppose. Especially since the space optimization, I don't know. Like, how do you, this is just inconsistent. I don't know, this is, anyway, yeah, that's all I have with this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.